Let's look at a commercial kitchen right after service. To the naked eye, this stainless steel prep bench looks completely spotless. But if we switch to an ultraviolet lens, a different reality emerges. What looks clean is actually a thriving landscape of biological contamination. Hospitality operators must engineer every cleaning cycle as a rigorous, verifiable hazard control mechanism. Relying on visual spot checks is guessing. Genuine compliance with the Hazard Analysis Critical Control Points framework, or HACCP, forces a kitchen to shift from subjective assumptions to objective, quantified data streams. To see how this works in practice, we can strip a high-volume commercial kitchen down to its physical geometry. This wireframe is the baseline, before any cleaning data or legal parameters are applied. Operating a commercial kitchen under modern FSANZ standards requires provable systems. If you want to survive an audit without triggering non-conformance penalties, every cleaning action must be supported by mathematical proof. The 7 principles of HACCP are often treated as a static legal document, resting in a binder in the manager's office. But to be effective, these rules must dictate the active, physical workflow of the kitchen floor. Principle 1 analyzes hazards: biological, listeria; chemical, detergent; and physical, metal fragments. Principle 2 identifies critical control points, like slicer blades and coolroom gaskets. Finally, Principles 3 through 5 mandate strict limits, triggering an immediate re-clean if a surface tests above safe thresholds. This structured approach is a legal requirement. FSANZ Standard 3.2.1 mandates that specific food businesses systematically identify potential hazards and implement documented controls. In New South Wales, the Food Act 2003 gives inspectors the power to audit these controls. Their most frequent target is missing documentation, which routinely results in immediate $880 on-the-spot fines. A written food safety policy accomplishes nothing in a vacuum. Its abstract principles must be rigorously engineered into the daily, physical actions of the kitchen staff. Applying the exact same cleaning intensity to every surface in a facility is a failure of HACCP risk assessment. Let's map the risk geometry. High-risk critical control points, like raw protein stations, demand maximum intensity, a 400 parts per million sanitizer, and verification below 50 RLU. Medium-risk zones, like general prep benches, only require a 200 parts per million sanitizer and a 100 RLU limit. Cleaning frequency is scaled by these exact risk tiers. The cooking line requires heavy degreasing and sanitizing after every single service, while cold storage units require a complete weekly strip-down and temperature log check. Neglecting non-food contact zones carries severe secondary liabilities. Ignoring exhaust hood maintenance directly voids fire safety compliance and commercial insurance, while failing to pump out the grease trap quarterly invites massive EPA fines. An audit-ready kitchen optimizes its labor and its safety simultaneously by allocating chemical strength and cleaning frequency strictly according to this calculated risk geometry. The selection of cleaning agents is a mandatory hazard. Without proper TGA and FSANZ food contact clearance introduces direct contamination to prep surfaces. Staff mixing errors are a critical vulnerability. Manual underdilution creates a weak solution that washes over a resilient bacterial biofilm, leaving pathogens entirely intact. On the other end of the spectrum, manual overdilution creates an immediate chemical hazard, leaving a toxic, unrinsed residue directly on food contact surfaces. Field testing shows staff manual mixing creates a massive variance, from 50% understrength to 300% overstrength. The only acceptable engineering control to eliminate this variance is a calibrated auto-dilution system mounted at each station. To verify chemical efficacy, we use ATP bioluminescence testing to detect microscopic organic matter. If the swab returns a digital readout over 100 RLU, the decision gate forces an immediate re-clean, extended contact time, and a reswap. Aggregating 12,000 swab results over an 18-month period reveals a 94% first-pass success rate across Sydney restaurant portfolios. The remaining 6% trigger an immediate corrective action protocol, providing auditors with statistical evidence that the system actively identifies and remediates failures. Substituting subjective visual checks with empirical RLU data and precise chemical parts per million is the only scientific way to guarantee a neutralized surface. A flawless system still relies on human execution. Cleaners must be explicitly trained to interpret safety data sheets and conduct precise ATP swabbing protocols. That execution has to be recorded. The traditional method, a disorganized paper logbook with a single vague tick, is consistently rejected by regulators. Compliant reporting requires a structured digital dashboard detailing the timestamp, operator ID, chemical batch number, dilution ratio, and the final ATP score. A piece of paper that just says "kitchen cleaned" with a signature tells an auditor absolutely nothing about the efficacy or safety of the operation. Ultimately, it is an assumption, not actual proof. Logging this specific data costs roughly $45 more in administrative time per clean, but that minor cost acts as a high-return insurance policy, allowing operators to generate a flawless 12-month auditable history the moment an inspector walks through the door. The ultimate legal reality of a food safety audit is incredibly simple. If a cleaning action is not documented with granular, time-stamped data, legally it did not happen. When executed correctly, a rigorous cleaning program acts as an early warning system for hitting structural defects. A localized cluster of repeated high ATP failures on a specific shelf serves as diagnostic data. If the surface continually fails at swab test despite repeated chemical intervention, the data points directly to a mechanical issue, a hidden condensation leak from a faulty evaporator housing dripping onto the stored product. We see the exact same diagnostic value on the floor. Recurring biological films in floor drains point directly to an overloaded grease trap capacity rather than poor mopping technique. Operating a verifiable system prevents wasting cleaning labor treating the symptoms of a mechanical failure. It forces the operation to identify and address the root cause. Quantifying cleaning as an auditable compliance mechanism satisfies FSANZ regulators and builds a protective barrier around the business, guarding against microbial hazards, hidden facility decay, and regulatory fines.